In this lesson, we are going to talk about combinations. Combinations are similar to permutations as we're trying to find the ways that different items fit together in multiple ways, only combinations are where order does not matter. Permutations, order did matter, combinations not at all. So a combination is a selection of things in any order. If you'll refer back to, we'll get to that in a minute, forgive me. If no letter can be used more than once, there is only one combination of the first 3 letters of the alphabet. You'll notice that the first 3 letters of the alphabet are written in 6 different orders. So that's 6 permutations, but because it's just the same letters rearranged, it's the same combination. So this is one combination. It's considered to be the same combination of A, B, and C because for combinations, order does not matter. So if you have A combined with B and combined with C in any order, it's all the same combination. In the list of the 60 permutations that we had in the previous lesson, 3-letter combos using the first 5 letters of the alphabet, each combination is repeated 6 times, so just like this. Within those 60 permutations, the number of combinations was 60 divided by 6. So within those 60 permutations, you actually had 10 combinations because you had 10 sets like this, where there were lots of 6 different orders of the same 3 letters, but because order doesn't matter, this is considered one combination. Same 3 letters, just different orders. Okay? So the formula for finding a combination is slightly more complicated than that of a permutation, but we will talk through it. The number of combinations of n items taken r at a time is, we would write it as NCR. Permutation was with a P, combination is with a C. It's going to equal n factorial divided by r factorial times the quantity of n minus r factorial. So, if we talk about those first 5 letters of the alphabet, taken 3 at a time, I told you that there were only 10 combinations. So let me prove it to you mathematically using our combination formula. 5 letters taken 3 at a time. If I plug it in, it's 5 factorial divided by 3 factorial times 5 minus 3 factorial. What that comes down to, 5 minus 3 becomes 2 factorial. So it would look like this. 5 factorial divided by 3 factorial times 2 factorial. Okay? Now I can, because of properties, commutative properties of multiplication, etc., I'm allowed to go ahead and simplify now while everything's broken down. I've got 3, 2, and 1 here. So if I wanted to go ahead and simplify here, I have 5 times 4 divided by 2 times 1, which I can just say is divided by 2. 5 times 4 is 20. 20 divided by 2, well, that's going to give me 10. And I told you that within those 60 permutations, there were only 10 combinations. Mathematically, this is why, and we will talk about that more at length. Let's talk about finding combinations. So a gourmet pizza restaurant offers 9 topping choices. Obviously, when you're ordering pizza, the order doesn't matter. It's not like finishing a race. Okay, if you have 9 different toppings and you want to get 2 toppings, the combination of those 2 toppings, doesn't matter which one comes first. So this is why it's under combinations, not permutations. Find the number of 2 topping pizzas that can be ordered. So we would solve this using the combination using 9C2 because we're talking about 9 different toppings that we can choose from, and we're taking 2 at a time. So this is 9 factorial divided by 2 factorial times 9 minus 2 factorial. 9 factorial is obviously 9 times 8, 7, 6, 5, 4, 3, 2, and 1. That is divided by 2 factorial, which is 2 times 1. And then 9 minus 2 factorial, 9 minus 2 being 7, so 7 factorial. So 7, 6, 5, 4, 3, 2, 1. I'm going to go ahead and do some simplifying here for the heck of it. 7, 6, 5, 4, 3, 2, 1. So I have 9 times 8 divided by 2. 9 times 8 divided by 2, because 2 times 1 is simply 2, right? And that's 9 times 8, not in 0.8. 9 times 8 is 72 divided by 2, and 72 divided by 2 is 36. So I can say that the number of 2 topping pizza combinations I can get if there are 9 toppings available, 36 different options. Okay? Find the number of 5 topping pizzas that can be ordered. Well, more toppings. We still have 9 that we can choose from, but now we are only concerned, now we are going to try to see how many 5 topping combinations are possible at this restaurant. So we're going to say 9C5, and so that's going to be equal to, now refer back to your formula to maybe help me write this. It's going to be 9 factorial divided by 5 factorial times 9 minus 5 factorial. Quite a bit of work here. It's going to be kind of ugly, but we've got to work it out. So that's 9, 8, 7, 6, 5, 4, 3, 2, and 1. All divided by, well, 5 factorial is 5, 4, 3, 2, 1. That's your 5 factorial. 9 minus 5 is 4. So this is 4 factorial, 4, 3, 2, 1. Okay. I'm going to do a little bit of simplifying again. I'm going to take my 5, 4, 3, 2, 1. Then, I know that 2 times 3 is 6. So if I cross both of these out because they're 6, I can simplify that 6 away. Pretty cool, right? So technically now what I have is 9 times 8 times 7 divided by 4 times 1, which we can say because of the multiplicative identity is just divided by 4. If I solve all this out, I'm going to get a total of 126 possible 5 topping combinations at this restaurant, given that there are 9 toppings to choose from in the first place. Lastly, we have these 2 additional examples. Different scenario now. We are moving away from pizza, which is going to be a very common example. We're talking about a group of 8 people. These 8 people are forming several committees. No one is necessarily the leader of these committees, just 3 people put into a group to form a committee. So find the number of different 3-person committees that can be formed. So order doesn't matter here, so we are going to use combinations. So there are 8 people, and we care about 3 at a time. So it's going to be 8C3. And as we write that out, I know that's 8 factorial divided by 3 factorial times 8 minus 3 factorial. So that's 8, 7, 6, 5, 4, 3, 2, and 1. Then 3 factorial is 3 times 2 times 1. 8 minus 3 is 5, so 5 factorial is 5, 4, 3, 2, and 1. I'm going to do my simplifying now like I've been doing. Again, 3 times 2 is 6, so I'll do that simplifying as well. So all I'm left with is 8 times 7 divided by 1, so 8 times 7 is 56. So it's 56 committees that can be formed of 3 people each out of 8 total people. Cool. Find the number of different 5-person committees that can be formed. So we're working with 8 people again, but this time we care about 5-person combinations. Order doesn't matter again, so let's see. If it's 8 people total, 5 at a time, that's 8 factorial divided by 5 factorial times 8 minus 5 factorial. So that's 8, 7, 6, 5, 4, 3, 2, 1, divided by 5 factorial, 5, 4, 3, 2, 1. 8 minus 5 is 3, so 3 factorial. 3, 2, 1. This seems familiar. Weird. So I'm going to simplify where I can. 5, 4, 3, 2, 1. 3 times 2 is 6, so I'll simplify with that 6, and I'm left with 8 times 7 over 1, which again is 56. Now that's strange, right? Because this is a completely different situation. Why does this work this way? Well, if you notice, this was 8 factorial divided by 3 factorial times 8 minus 3 factorial. 8 minus 3 factorial turned out to be 5 factorial, so our denominator was 3 factorial times 5 factorial. Jump down here, we ended up with 5 factorial times 3 factorial in our denominator. So our denominator just had a little bit of commutative action going on, therefore we ended up with the same result. Sometimes that happens, sometimes it doesn't. But that, in a nutshell, is combinations.